I've got the difficult task to be the last one of the day, so I hope you fit very well. Today we'll be presenting the LoCod software, which was developed by CNES under R&D contract. We will follow a basic top-down presentation and content. Basically, a short overview about CNES. We are the French space agency. We are built about 3 pillars, the technical one, the legal one, and also operational center, which is quite unusual for agencies, especially in Europe. And I'm working especially in the data handling department, handling everything from computational onboard computer for space vehicle. The LoCod framework was developed, please acknowledge that, by Viveris Technologies, and they are currently maintaining the tool as an open source software. So basically, what we are facing is that we, on the general point of view, we are putting more and more features into FPGA and into embedded stuff. We have to see that there's an amazing presentation today. We are speaking about quantum computer, we are speaking about AI. If you went a couple back years ago, it was FFT or filter and so on. So we put many more stuff, and this provides a lot of trouble. And this is especially due to the fact that, and I'm speaking for the space point of view, we are I've got more powerful FPGA, system on chip available, and even network on chip, or ACAP as Xilinx is calling it. And we are working on both sides for space application. One is a commercial part device, like you are using, I think, for your detectors, like Xilinx stuff and so on. And we are also working with radiation hardened by design, like NanoXplore chip, which is developed in France under European funding development. And these are the new feature we've got recently, because we used to use micro-semi anti-fuse FPGA for space, which was quite smaller. And now you've got with these Versal devices, you've got tons of processor, you have AI engine accelerators, you've got DSPs, you've got FPGA, and even embedded DDR memory controller. So basically, to face this kind of increase in features, when you are developing an algorithm, you are facing a trouble to be able to fit perfectly your algorithm into this kind of heterogeneous architectures. And this is really easily achievable by, it was easily achievable by FPGA designers back then, but now with processor involved, with FPGA involved, with DSP involved, with massively parallel processor involved, you have to get more competence to address this kind of feature. And this is what codesign is meant for, is that you have to, for an algorithm, a selected algorithm, you have to select which part you are going to do in software, which part you are going to do in FPGA, or offloading in another external accelerator. And this has to be some kind of exploration. And sometimes when you face some trouble in performances, achieving your goals, you have to go back to the main original algorithm and even change it. And it's common feature, like now for EA, you say you are changing the weight of your algorithm. So what is LoCod? LoCod is an acronym for logiciel de codesign, for the French guys. So if I may translate it, it's like a software codesign framework. Basically, what LoCod provides is that at first you are developing your algorithm for an embedded target, and then you use a specific C API. It means that you are forcing yourself to encode all your input in structures and all your output in structures, and to isolate your the main part or the main function of your algorithm you want to offload into a function. And then on the other side, we provide some kind of infrastructure in the FPGA to be able to get as a shell to put where you will be able to put your accelerator into it. So how you are going to use it? It's quite simple. It's based on Docker images and lots of scripts. Basically, LoCod is no more than a framework. There is no tool really developed in it. It's just something it's supposed to be facilitating the developer of an algorithm. You simply have to write your C code for embedded stuff and then launch a script and target one of the boards which are currently supported. There are some from Xilinx, Zynq UltraScale Plus, and from NanoXplore board also, and NanoXplore and Medium, and then flash it onto your FPGA. You will, in more detail, how you are going to use it. So as I already told you, you simply isolate your function, and in your function you put your input parameter into the structures. And what is the beauty of LoCod? It's rely on HLS tool, and then we are going to look for this function, and we are going to translate the feature of the encoded function with HLS directly into VHDL. So we'll be able to put that like a kernel into your FPGA, and then we take care about all the exchange between the software and the FPGA automatically. How it's working? Basically, it's LoCod is in the middle. We are relying on two open source technology. The first one is the more common one for embedded development, which is GCC. And you are developing your algorithm for an embedded target, and then you put all the software stuff into the GCC branch, and then GCC is compiling your application and creating this executable, and this executable will be run onto the processor part. And on the other side, if you want to offload one of the features, you simply have to call some function called FPGA offloading function, and this specific C code will go to the branch into what we call PandA. PandA is HLS open source tool developed by an Italian university. And PandA is basically like Vivado HLS, but without Vivado and without the closed source feature. It's relying on LLVM, and then it's creating the VHDL code source, and then you can call your favorite synthesis tool, like NanoXplore if you want, or Xilinx or Altera. And then you will get your FPGA design, and you'll be able to put that in your system on chip, or at least an FPGA embedding a processor part and a VHDL part. What's in LoCod? In LoCod, what we put is that we rely on a CPU like the main processor, and your main code will run onto the CPU, and this CPU is going to discuss with the FPGA with a shared memory. So this is not a DMA memory as we FPGA developers are used to. It's not an engine which is going to transfer data and offloading the processor. It's more like a dual port memory which is shared between the CPU and the FPGA. And then instantiate also a bank of registers which are mostly the control feature of your kernel or offloaded algorithm. And then when you run into your software, if the function was supposed to be executed in CPU, it's working like a normal function in the CPU. And then when we are offloading the kernel into the FPGA, we are calling a specific function which are offloading data into a shared memory, and then use the register to start the accelerator, which is performing its work. You can do in software everything you want in the background, and then wait or have some kind of synchronous function, which are implemented in LoCod, waiting for the result of your accelerator, or one or as many as you want. we did some kind of experimentation for LoCod. So the one you are seeing there is included into the repository for host on GitHub. And this simple application is based on the Bayer matrix, which is not usually when you've got a pixel, you've got RGB on one pixel. In the case of Bayer matrix, you've got red pixel, green, blue, and dispatching on a bigger size, and then you have to translate and to apply some kind of transformation function to go back from this square to recreate the RGB pixel at each location. So it's basically matrix application. And then we included everything into the GitHub page. You've got the MATLAB source code, which is a reference model, and you've got also the implementation in C for embedded program, and then the implementation with the offloading of the transformation into the FPGA. You are not going to see performances different. This is not the main. This was not the main objective when we developed LoCod for the first iteration. It's because we want to give people which are involved in the development of algorithm the possibility to address architectural change, which we call the design exploration, architectural change in their algorithm, and to evaluate what would be the benefit of offloading into an FPGA in terms of computational time. What we are going to do for the next step, so everything is released. It was supposed to be released current of this month, so it was done earlier. So congrats, we are already online from now. We've got full support for Zynq UltraScale Plus target. We run into some difficulties to NanoXplore. I don't really like the bottom down finger, but anyway, this is an ongoing development. We started LoCod at the same time as NanoXplore released its system on chip called NG Ultra, including R52 processor with an FPGA matrix. Everything radiation hardened by design. So it's quite a work in progress. We will continue to improve LoCod, especially regarding the support of NanoXplore, because we are working in the space environment, and for us, NanoXplore is a priority as a target FPGA and system on chip. And we will try to increase also the performances of the transfer between data between the processor side and the FPGA side, in order to be able to prototype more efficient algorithm. Anyway, if you want to try, you can try LoCod online. You just have to flash the QR code if you want to go directly to the GitHub. And feel free, if you are interested, to go back to me or to the Viveris team through the GitHub or any other channel. So we'll be glad to answer your questions. Thanks.
Thank you for the very interesting talk. You touched on that in the conclusions, but I wanted to ask you to elaborate a bit more how you transfer the data between the logic and the processor, because it's an interesting problem where speed is.
There was the same feature, I think it was in Chebi tools described yesterday. It's almost the same feature, actually. When you move the data, you've got in your structure, you've got I would say the control path and the information which are stored in the register over there, and then you've got what we can say the data path, which is mostly some kind of dual. It's memory exchange, actually. So you are putting the data into a memory which is going to be accessible by the FPGA and by the processor. So at first, the processor is writing stuff into a memory. It can be a processor memory like DDR, or it can be a BRAM, depending on the size of the data you want to transfer. So it's up to you to define that. And these are typically configurable using PandA interface, like a normal HLS. You define your interface for memory, so you can define an external DDR which is shared, or you can define an internal BRAM, and so on.
Thank you.
First of all, nice presentation, a nice tool as well. Yeah, following up with the question about the interface between CPU, well, the PS and the PL. How does this interface perform compared to other interfaces like XRT? Because XRT is also C, well, you have C bindings, but it's a C++ library. Yeah. And also, what's the experience with respect to pandas? For instance, if I code the same kernel in pandas compared to HLS from BTs, so how does it perform?
You mean in terms of performances or accuracy? Or?
Yes, performance overall. Yeah, at the end you have HLS, so convert C++ or C to HDL. So
I didn't run into any test bench for PandA. I think you can go to the website. There are plenty of it. PandA is an academic tool, and so I think this is the same differences between any academic tool and any commercial tool. You can do things manually, lots of things, but they won't achieve a high level of performances. But it will be doing the job, depending on what you want to achieve. And for the first part, I don't know XRT interfaces, but we are not focused about the performances in this use case. So this is the next step. We are going to improve stuff. And so that's why I don't present any performances, timing gain, because this was not really our purpose. Our purpose is to almost train the algorithm, the scientist, to achieve quicker decision about this algorithm, because it's quite complex for us, and it should be for everyone. I think you've got the guy with the knowledge of the algorithm, of the science part, and then you have to translate that into an architecture, and it's usually different people, and if you have got some kind of bottleneck, you cannot make your own decision as a designer because it relies on performances and on the scientist side, so you have to go back to him. So that's the thing we want to improve and smooth stuff, and maybe people will do the rough job with this tool and then go back to their particular infrastructure to do dedicated work on the HLS and dedicated work on the embedded software.
Yeah, I was asking that because I have been playing with this problem of transferring data from PS and PL. I was basically working with XRT, but for instance, I have been doing XRT and also PinQ, but it resulted to be, when I translated the PinQ code into C, it resulted to be faster than XRT. So at the end, I ended up with a new framework. So basically, to take advantage of both worlds. So having C with lower latency compared to Python, but with the easiness of Python. So probably we can talk about this.
But in any way, we will not rely on any vendor-specific accelerator, because we want to target NanoXplore and Xilinx and maybe Altera also.
Yeah, you have the same goal as me, as mine.
Okay, thanks for the great talk. My question is about the compilation time, actually. And when you make a change into one offloaded function, do you recompile the whole firmware, or is incremental?
Sorry?
About the compilation time.
There is no comparison time, actually. Right now, we embed into the IXC register over there, we embed some kind of timing function a counter, which is basically counting from the start of the kernel and the end of the kernel, and then you get the metrics over there. But we didn't include any performances for the data transfer because we didn't work on that.
No, sorry, I mean when you have the program and you produce the firmware.
When I produce the firmware, yeah.
Yeah, and there is a basic HLS compilation.
There is a
HLS synthesis.
yeah.
And about that time, does it firmware add any overhead to the HLS and the C compilation?
With you mean with the embedded software, the two
Yeah.
algorithms? Yeah, not really.
Not
Actually,
really.
because that's why I was saying that on the embedded side, you can rely on the processor counter, time counter, and on the FPGA side, we rely only on timing counter for execution, which is embedded into the IXC register, but we exclude the transfer of the data from this evaluation, which is part of the algorithm.
Yeah, actually, before everything is running, just compiling.
Just compiling? It's like, sorry, I was on the other side.
Compilation time.
Yeah, compilation time, yeah. No, I've got no number about the compilation time, but I did some try with PandA Bambu, and it's quite fast. It's like almost any HLS tool. Many of the HLS tools are quick to translate in VHDL, but depending on the size of your accelerator, it will take ages to synthesis and plus en route.
Yeah, and when you change something, in your offloaded function, do you need to recompile the full
everything,
firmware?
Yeah.
Okay.
Yeah.
Thank you.
I've got a quick question, actually. Are you targeting a specific, like a space mission, a specific satellite to try this out, kind of targeted, creating the bit files that actually go on the mission to space? Or
If I may target it, sorry?
Yeah, are you using this for any particular
No.
satellites at the moment,
No,
or are you
it's
targeting a specific?
It's
one in
R&D.
5 years' time?
No, it's R&D development.
Okay.
For now on, and we
Yeah.
will improve the tool. And for any application right now, it's quite complex because with the change of usage into the FPGA, all this kernel stuff, and the arrival of the Versal architecture for us, and lots of AI stuff will be embedded on board, and we are quite looking for the methodology to achieve that, and our people and our scientists will be working on their algorithm to embed stuff. So it's more like we try tools, and then when they are starting a project, we say, we've got this available, and then if you want, you pick it, or you don't use it, you take another one. But we have to get plenty of available choice under our choose, and so people be able to select one. But most of the time, this kind of tool might never be used at all. Just internally
just
for
used
us.
for the design process,
Yeah.
and okay, thanks. No other questions? Okay.
Thanks a lot.